Good. So now I'll share screen. So we started doing the started analyzing the propagation of a wave in a medium. So this is where we're at actually. We introduced this idea of a quasi-monochromatic wave, which leads to the concept of polarization fraction. So that's the idea that when we have near perfect monochromatic waves, then these monochromatic waves actually have a polarization fraction. They're not necessarily polarized. Okay, so that's what we did last time, and now I would like to consider what happens to a monochromatic wave that propagates inside a medium in which we have constitutive relationships. So I need you to say when I mention something that's new to you. If there's something that you've not heard of before, just say so, and I'll try to explain. So when we have a medium, the medium in electrodynamics is described, physically speaking, the medium is described with these constitutive relationships. So we have the electric susceptibility, which connects the polarization of the medium with an external electric field. Okay, so the polarization is the density of microscopic dipoles. Okay. So you can think of it this way, that P is n times one little dipole, you know, like where would have like atoms or molecules, and each one of them would have like this a dipole like this. Okay, and of course the dipole is a charge times a displacement. Okay, so maybe you could add like an average over all dipoles in a gaseous medium. Okay, so that's the polarization, and then we also have a relationship. So the polarization is proportional to an applied electric field. Okay, and this is something you should have heard of before. If this is completely new, please say so now. Okay. So another important property is the magnetization, which is very similar, where we have this density of small magnetic dipoles. Okay, and we can connect the magnetization with the applied magnetic field, which in a standard development, which I won't be repeating now, leads to this idea that we have a relationship between mu and H. Okay, so H includes the magnetization. In other words, I can't remember exactly what the relationship here is between B and H. Just have a memory hole here. But what I'm trying to say is that B includes, this is the total B field, including the magnetization, so the microscopic dipoles, and H would be the magnetic field caused by the currents only. So anyway, you've seen these relationships before, and the relationship between P and E, and the relationship between B and H. So by the way, this one leads to the displacement vector, which is epsilon times E. Okay, and maybe this is the best way to put it. So these two relationships here, these two relationships over here are called the constitutive relationships because they connect the displacement vector and the magnetic field with the standard form of the electric and magnetic field in vacuum, taking into account the medium. Okay, and so these are the permittivities, the electric and magnetic permittivities. Okay, so we can add to these equations, we can add the Ohm relationship, Ohm's law, really, where we have a proportionality between the induced current and the applied electric field, and so that would be the conductivity. Okay. So now comes I think this should be fairly standard to you, but now comes the trickier part, and it's a look at equation 53 in my slide. We will write them again, but not in terms of the standard signal for B or E or J, but rather in terms of their harmonic decompositions. So here the idea is to say that, for instance, look at the magnetic field. The idea is to say that the magnetic field is a signal, B of t, and then we will be decomposing spectrally this signal, by taking the Fourier transform, etc. And so each harmonic component of B should also respond to a constitutive relationship. Okay, and we could also decompose spectrally the magnetic susceptibility. Okay, so we take B of omega, we take mu of omega, and we take H of omega. Okay, and we say, well, it's just the same as the total signal. Each one of these harmonic components should be related in this sort of constitutive relationships. So this is a bit of a leap, if you want, because one thing is to cast the constitutive relationship in terms of their total signal, and this is another thing that we are looking just at one spectral component. Strictly speaking, I should be taking the Fourier transform or the spectrum of the product of mu and H. But here I'm appealing to your physical intuition to imagine just a monochromatic signal. So suppose that we have just one monochromatic component, or quasi-monochromatic component, but just one omega. Then in this case, there will be a magnetic susceptibility connecting B and H for that particular monochromatic component. Okay, so what I'm trying to say is that suppose that we have just one monochromatic component, there will be a relationship connecting H and B for that monochromatic component. And that relationship is called the constitutive equation, and the proportionality is given by this permittivity mu. Okay. Any questions so far? Or assume not, unless someone says so. Okay. So that's new. Equation this part of the of equation 53, in which we apply the constitutive relationships to particular monochromatic components. Okay. Each of these quantities, chi, mu, and sigma, must be real. For instance, here for the electric susceptibility, then we need this hermeticity relationship, so that the total signal in the function of time is real. Okay, so and similarly for mu and sigma. So all of these quantities, chi, mu, and sigma, are real in the for the signal, and the spectral components are emission, is what I meant to say. Okay. You realize, you recognize here the Fourier transform of the spectrum. Okay, so we have the Fourier pair. Let me write it down. So we have chi of omega equals to into r dt and so that's one way to write the Fourier pair, and I'm saying that this is real. Okay, therefore the susceptibility, the harmonic susceptibility must be emission. Okay, so now comes a very puzzling property of this harmonic of these harmonic relationships. So now this is quite tricky to follow, and it's also quite tricky to explain. I'll try to make this to explain this in a concise way. So remember the convolution theorem. Like if we have a product of in Fourier space, when we have if we say X is the product of Y and Z, then in real space, X would be the convolution of Y and Z. So this is the Fourier convolution theorem, which I'm sure you must have heard of. Okay. So if we apply this convolution theorem to chi, for instance, okay, let's write down chi again. So what was chi about? We have this relationship. We have chi. Let me write it down so we can have it in mind. So this is P, the relationship in P and E, and we're saying that then the harmonic components must be related this way times E. Okay, so we apply the convolution theorem to that part. Okay, and we say but then the real signal, if I write the product here in Fourier space, then P of t can be written as the convolution over time of epsilon 0 chi times t minus t prime times E of t prime. Okay. I'm just applying the convolution theorem for now. Okay. And so this would be what's called G t minus t prime in equation 55. Okay. I'm just identifying G t minus t prime in this equation here. Okay. And then we can also write this G minus t prime as this is G minus t prime, then G of t is then epsilon 0 chi of t, And we have just seen that this one is related to the spectrum of chi. So it's 1 over 2 pi times the integral of omega of chi of omega e I omega t. Okay. So basically, we are applying the convolution theorem to the case of the susceptibility, for example, okay? And we notice something. We notice that we can write P in terms of the convolution of some kernel G with the electric field over all times. So now that's kind of intriguing, isn't it? Because if you look at this relation, we are integrating to obtain P of t, we need to integrate over all times. With this dt prime goes from minus infinity to plus infinity. Okay, so now that's kind of weird because how can we have the polarization at some time t depend on future times? Realize that there is a problem here. You know, like the way this is written here, we see that the polarization at some time t will depend on the whole history of the electric field. So necessarily that's not possible. We cannot have something happen at present that depends on the future configuration. Okay. So we need this kernel G of t times minus t prime to be 0 if t prime is greater than t. Okay, so we need G of t to be 0 if t is negative. Okay, so that's an if. So this is a causality relationship. Okay, we require G of t to be 0 for negative times in order for this relationship to have physical meaning. Okay, so we will expand on this later on to write down the Kramers-Kronig relationships. For the time being, just bear this in mind. You know that there is this intriguing fact. You know that an application of the Fourier convolution theorem tells us that the polarization at time t would depend on the whole history of the electric field, including the future development. Okay, and so that cannot happen. You know, so going back to the monochromatic waves, in this case now we'll be writing the electric field as in this way. You know, like so this is the electric field. We are doing the real Fourier harmonic decomposition. Okay. So we decompose it in terms of a cos and a sine without loss of any generality. And this would be the real part of a complex electric field. Okay. And in order for the real part to look like this, you know, one can propose this expression for the complex electric field. Okay. So that would be the complex electric field whose real part corresponds to the expression I'm writing for the monochromatic wave. Okay, so if this is the monochromatic wave, then when I take the spectrum of it, when I Fourier transform this monochromatic signal, I get this spectrum. Okay, so we have delta functions. And the spectrum is just 2 spikes, you know, like this. So we have 2 delta functions at omega 0 and minus omega 0. Okay, so that's the spectrum for this monochromatic plane wave. Okay, so if this is the electric field, then we can calculate the corresponding polarization. Now here maybe I forgot to stress that when we say the medium polarization, we mean something completely different from the Stokes parameters, right? Okay, So the Stokes parameters refer to the polarization of the wave. This is the polarization of the medium. Okay, of course, just there's two different things. Okay. So the polarization is given then by this relationship we've just derived, which is so that's the Fourier transform of the product in the Fourier domain. So let's go back here. Just reminding you that I'm using this expression P of omega. That would be the spectrum of P. Okay, so I'm taking the anti-Fourier transform. I'm using this relationship for P. Okay, so this would be P of omega, and I take the Fourier transform to take it back to P of t. Okay. So since we have delta functions, this is quite easy to evaluate, you know, and we are left only with the susceptibility at the harmonic frequency. Okay. And of course, we always have we always take only the real parts for the physical signal. Okay. And in this final expression, we've used the fact that the other component, the other delta function, can be related to the previous one using the hermeticity of the susceptibility. Okay. And so yeah, so this would be the polarization related to this monochromatic wave. Okay. Now let's go back to the Maxwell equations. So we can write. Sorry, I think I added a homework here because it's not. I think it's necessary for you to do this this development. So I've added this little career here for you to demonstrate this part. It's not easy. Sorry, it's not difficult. It's easy to do. So the idea is to simply take the Maxwell equations. Okay, so we have the Maxwell equations are these ones, and then you plug in the spectral decomposition. So since we are talking about the medium in the absence of free charges, so this is 0. Okay, and since these all these vectorial operators are linear, we can exchange them with the Fourier transforms, and each of these equations can be written into the Fourier domain counterparts. Now the difference comes from the time dependence here. So the time dependence of the magnetic field, for instance, will yield an I omega when you differentiate. And likewise for the electric displacement, which will also yield a I omega. Okay, so these Maxwell equations can be written in this way for a for the Fourier components. Now, it's important to realize that this epsilon here, the which gives us then the proportionality between, well, you know, this epsilon that goes into this equation is actually expanded this other way, okay, which is related to the electric susceptibility. So that would be the standard part, but it's also including a conductivity term. Here I'm also using Ohm's law, okay. So the electric permittivity is given by a real term and an imaginary term. Sorry, this is a complex number because we're talking about the spectrum. Just meant to say that the electric permittivity is composed of, well, the standard susceptibility, the electric susceptibility. It also includes the conductivity, okay? So it's got an imaginary part, and the imaginary part is given by the imaginary part of chi, and including sigma over omega. Okay, omega is real, of course, it's the frequency. Sigma is real, it's in Ohm's law. Okay, but chi could be sigma, strictly speaking, could be complex too, because we're talking about the spectrum of it. But chi, well, what I mean to say in the end is that the electric permittivity is a complex number, and that's the imaginary part. Okay. I'll now talk about, again, this causality issue. What happens with these causality requirements, okay? So, the idea here is to show how causality eventually has an important consequence between the real and imaginary parts of the constitutive relationships. So we'll see that the Kramers-Kronig relationships allow us to establish relationships between the real part of the refractive index and the imaginary part of the refractive index. So to start, let's try to forget a bit what we've just done and look at it from a physical point of view. So we have some material, and we apply an electric field. Okay, so imagine that we have a block of dielectric, and it's happily sitting in free space, until an experimentalist comes and applies an electric field. Okay, so we have like in the time dependence of this would be like E of t we have a step function. Okay, so all of a sudden we have an electric field, and then maybe the experimentalist could shut it off at some times t0, and this would be 0. Okay. So in the medium, we have some polarization, okay, induced by this applied electric field. The polarization is going to be 0 here, 0, 0, 0, 0, 0. And then we have this electric field, this applied electric field. And the medium will respond to it, So polarization will increase and yield some, and go to, some steady state value. But it's not going to be instantaneous. So that would be P of t. Okay. And when we shut off the electric field, well, the polarization is also going to decrease, back to 0. Okay. But there is a delay. So what I'm trying to say here is that the response between the electric field and the response from of the polarization to the applied electric field is not instantaneous. It depends on the history. And so when we write it down like this. We say that the polarization at some time t will depend on the history of the electric field with some kernel G. We don't know what G is yet. Okay. In principle, this kernel depends on the time where I'm evaluating the polarization and the time over which I'm integrating the history of the electric field. Okay. So like inherent in this is the idea that the polarization is epsilon chi e, but this is in steady state in electrostatics. In electrodynamics, things are dynamical and take time. There is a finite time there's a delay for things to adjust. And so that would be strictly valid only in electrostatics. Okay. Now I said that there is a difference with equation 55. That's broken. There is a difference with equation 55, which is this one. Because here I'm writing G as T minus T prime because of the convolution. Here, I'm not invoking the convolution theorem, sorry. I'm just using the fact that from physical consideration, there should be a relationship like this one. Now, for instance, we apply a delta function for the electric field. Suppose that we just have a pulse. We apply an electric field at some time t0, and that's it. Then the polarization given by equation 1662 is going to be just the product of this kernel and E0, okay? So G would be the polarization resulting from one delta unitary pulse, electric pulse, okay? And now the idea is to say that the this kernel, the time dependence of the time dependence of this kernel G times T0 does not depend. What I mean to say here is that if the medium does not, if the properties of the medium do not depend on time, then we can write this kernel as simply T minus T0. Okay, because that would be if the kernel, if the medium is not changing over time. I mean, if you have this dielectric, so that would be like the representation of this dielectric that is constant in time. It doesn't say, for instance, it's not expanding or it's not contracting or it's not changing shape or it's not changing composition. If this is if the physical properties of the medium are constant in time, then the kernel can be written as simply not two arbitrary variables, but just one time dependence. Okay, and then again we say the causality argument, and so now we say that go back to question 62. We say that, well, we require this kernel to be 0 for future times because the polarization at some time t cannot depend on the future. Going back to this drawing and I've got here, the polarization here cannot depend on what happened after 0. I cannot say, this is the polarization was 0 here. So whatever the experimentalist will decide to do in the future, it's not gonna affect the past. Only the past can affect the present, but not the other way around. So this is causality. Okay. So what we're trying to say is that P of t, t minus t prime, E of t prime. Okay. And here we are integrating from minus infinity to plus infinity. And so for this to make causal sense, we need G of t minus t prime to be 0 if t prime is greater than t for future times. Okay. So that means that G of t, or maybe let's change variables, tau is 0 if tau is t minus t prime, and that's less than 0. Okay. So now, if okay, so now we have this property that the susceptibility can be written in terms of this kernel. Okay. So we have this expression between the susceptibility and G of t. let me see if I can remember how to prove this. Equation 55, we've just got it. It's yeah, it's this one. So it's P of t is the integral of g of t minus t prime times e of t prime. Okay. And then I have a tip here, which is using a harmonic field. So if the electric field is given by E0 e omega t, then P of t is the integral on or dt prime of g of t minus t prime times e of I omega t prime dt prime. Okay. And how do I connect this to? And now I need to obtain the oh, I see. So now I want to obtain the this susceptibility. So that would be chi of omega. I think I've got it written down. Yeah. And so we have that chi of omega is hold on a minute. Yeah, that's going to be the integral over dt of chi of t I omega t. Yes. Sorry. Now going back to this proof. Yes, and I have this this relationship between chi. Okay, and so we have that P of t is epsilon 0 chi of t times E0 I omega t. That's good. Since so that means let's see if I can get things right. That we have that means that that chi of t is the integral over dt prime of g t minus t prime times e to the I omega t prime minus t. I'm just taking the so I've replaced this at the left hand side. I've replaced P of t with epsilon 0 chi and the electric field, and on the right hand side I'm keeping this expression. Oh, I forgot to put the E0 here. Okay, so that cancels out with the left hand side. Still need to have 1 over epsilon 0 somewhere, I think. Yes, so let's leave it there for the time being. Okay. All right, and So I've got this integral is going from minus infinity to plus infinity. And then I think I should make a change of variables. Let's see. This was obvious to me when I saw it. I did so many times, but now I can't see it so obviously now. But yes, so this is t minus t prime, and this one is okay. So this is going to be wait. This is the opposite as this one. Okay, so this is let's call this minus tau. Okay, and this is tau. So that d tau is equal to dt prime. Okay, and this argument is 0 for when you know we said that the causality is requiring that gt is 0 if tau is negative. Okay, so we have finally that chi 0t is the integral of d tau of g of minus tau e omega tau. Okay, and that should be 0 if the argument is positive is negative. So when tau is positive. No, right. So when tau is negative, this is 0 when tau is negative. So it's non-zero when tau is positive. Okay, because of the minus sign that's here. So I've got a problem because it's not exactly what I was trying to prove. I've got the kind of t as a function of these. So sorry guys, I thought it was going to be easier. For some reason, I cannot easily recover this because this is a spectrum, and now on the left-hand side, I've got the real part. Maybe I overlooked something. It's a bit. Well, this is a little bit tedious. I'm sure it must be even more tedious while you try to follow me. But since we don't have much time left, let me just. Well, this is more or less the lines of the proof. One in the direction of the proof. I'll try to make this up for the next lecture. But to make a long story short, we have this expression for the spectrum of the susceptibility. Okay. Maybe I've just got a typo here, and this is T. I just need to check my lectures. The point here is that no, it was actually the complex plane. So the point here is even worse. So let me try to make this a long story short. We can prove this. I'll try to prove it next time because this should be easy to prove. But we have this expression there then for the that connects the susceptibility with this kernel G, and we can make a trick now, which is quite difficult to digest, and this is to extend this equation 63 to the complex plane. So now this is very academic, and I'm sure it must seem completely pointless, but we reach an important conclusion. So this is derived from causality, and we can extend it to the complex plane. And the point here is that this integral goes from only from the positive times, from 0 to infinity. And so the idea is to say that if the modulus of this integrand converges, then so does the product of the integrand times this oscillating exponential. And that means this expression allows us to say that this susceptibility is analytical in the superior complex plane for the imaginary extension. So I know that this is very arid, but it's just to say that we can apply the Cauchy's theorem, okay, and we'll apply it to this function chi of omega in the complex plane, and we're imagining a complex frequency, but it's just a mathematical construction, and we correct it for this divided by omega minus a point on the real axis, okay? And we say, well, this is analytical too, except in the pole, and this is basically, this allows us, this is a mathematical property which allows us to write down finally this equation 65, which says that the value on the pole is connected to the integral along the real axis of the omega. Big capital omega is just another integration variable that goes along the real plane for omega. And this p here is what's called the Cauchy's principal value, and it's a limit. So the principal value of this integral is the limit of the integral on both sides. So you see we have a divergence on omega, and so we come close to omega on both sides in this limit. That's called the principal value. So don't worry, we won't be doing principal values. I just want you to see what comes next, and this is it. And that this treatment, which I failed to prove the beginning, but you can imagine that it goes well. It's quite straightforward in complex plane calculus, but you finally get to these equations. That if you have this susceptibility, which has got a real and imaginary parts, then the real and imaginary parts are connected thanks to this equation. Okay, this I here mixes the real and imaginary parts, and this P is this limit as you do this integral diverges if you take it straight, but you can take the principal value of it, and that doesn't diverge. It's like taking the integral on both sides as you come towards the singularity. And you have similar relationships for mu and sigma. So these are the Kramers-Kronig relationships, and they connect the real and imaginary parts of all these constitutive quantities. So going back to the monochromatic waves now, we rewrite the monochromatic plane waves. So this you've seen thousands of times, but this time we will allow the vector the wave number, the vectorial wave number, to be complex, okay, and in some direction E. So this way we can write this complex electric field in terms of a damping component, which is due to the imaginary part of the wave number, and the oscillatory term is due to the real part of the wave number. So you plug this into the Maxwell equations. So these are equations, the harmonic Maxwell equations. Okay, you plug that in, and ends up with yielding these relationships between the electric and magnetic fields. Okay, and so you end up with this dispersion relationships that connects the wave number with omega. I think you must have seen this before, so that's why I'm going fast in any case. So when there are no free charges, when rho, the charge density is 0, then we can write K, well, yes, I mean, yeah, I was about to say that we can always write K in this way. It's just that when there are free charges, then the electric field is no longer transverse. There is a component towards the direction of propagation. But there are no, we're taking the case where there's no, rho is 0, basically. Medium is neutral, okay? And we define, in this case, this refractive index, this extension of the refractive index, which is the ratio of the sound speed in the medium relative to the sound speed in vacuum. Okay, so this is the definition of the refractive index, and it's got a real and imaginary parts. Okay, so when you use equation 70, which would be this one, when we plug in this complex wave number into the monochromatic wave, okay, and we introduce the definition for this complex refractive index, this is what the monochromatic waves is looking like. Okay, so we have a damping part which corresponds to the real part of the imaginary part of the wave number, and we have this oscillatory term which corresponds to the real part of the wave number, and that's the real part of the refractive index too. So it's standard to write a refractive index in terms of an n and a kappa. And now this is really important, even though I spent some time talking about the Kramers-Kronig relationship, which seems a little bit abstract. This is super concrete, and we need it in astrophysics when we talk about extinction, because this is extinction. You know, when you talk about the reddening and extinction, this is the responsible term is kappa, the imaginary component of the refractive index. And these Kramers-Kronig relationships connect the real part of the refractive index with the imaginary part. Okay, so here we have the connection between the imaginary part and the real part. Okay, so this is just to say that when we calculate the optical constants of a medium, so you know, in some concrete applications, you go to the so the table of optical properties to calculate your radiative transfer, and you want to calculate the cross section of the grains, for instance, and you want to calculate the opacity of the medium, then you're given these constants n and kappa. Okay, and now you've learned that they are connected. The details of how they're connected do not really matter for our concerns, you know, but just that the way this is calculated is like this. So basically, people calculate just the real part, and from the real part, they can extrapolate the imaginary part using the Kramers-Kronig relationships. We've gone over chapter 2. I'll very briefly summarize what I've just said next Tuesday, and then we'll go on with radiation at last. I realize that this is a little bit fast, and I'm sorry for this, but we barely have only like maybe 1 or 2 weeks left to finish the course. And well, that's what we could do in the pandemic situation, but I'll try to cover the most important parts of radiation at least. So I'll try to do this in the next couple of weeks, okay? With this, ciao, and see you next Tuesday then, okay?
Ciao, ciao.
Ciao, guys.